Good morning. I saw that Sanders posted the homework assignment. Looks real fun. Here's the attendance. Also, I should actually give myself a quick note here. All right. So I imagine you guys have all sorts of questions. I was thinking, I know someone asked me about global maxes and mins the other day, so I thought I would start there. So feel free to chime in though if you have other things you want to see. Obviously, there's lots of stuff on this homework assignment. So let's get going. So I'm going to do a couple 4 and 9. Sure. Yeah, Taylor polynomials are always super fun. Yes, we can definitely go over problems like those for sure. Taylor polynomials kind of something I got memorized, but we'll talk about that for sure. Derivatives of inverses. Yeah, we can talk about that too. So I guess let me start with derivatives inverses just because that's kind of some of our former stuff. It's kind of a pain in the butt. So if you want to find, so the very, very kind of general understanding this is that the derivative of the inverse function is 1 over the derivative of the original function evaluated at the inverse function. Now, usually we don't actually use this to find the derivative as a function, but the derivative, the derivative at a point. I need to change my video settings 1 second. There we go, much better. So for example, if you had a function, sure. Let's say our function was sine of x, which we do not know the derivative of the inverse. That's not something we do in this class. But we can find the derivative of the inverse at a point. So here's all the stuff I know. I know that f of pi over 6 is equal to sine of pi over 6, which is 1/2. So again, if I know sine of pi over 6 is 1/2, then I know the inverse sine of 1/2 is pi over 6. Okay, so what I want to do with this is I want to find the derivative of the inverse sine function at the point. Sorry, I have to think for just 1 second here. Yeah, at the point or at x equal to 1/2. Okay, so here's the idea. And so I think, so a lot of you, those of you that took the quiz, something a lot of you missed was actually taking the derivative of the function. So I know that to do this, I'm going to say, well, okay, I know that the derivative of the inverse sine function evaluated at some x is going to equal 1 over the derivative of sine. So I'm imagining that my function is sine of x, and my inverse function is the inverse sine of x. So what I'm going to do is I'm going to take the derivative of, well, I'm taking the derivative of sine, right? So I'm doing the inverse of sine here, and so I'm doing, right, that's my inverse function, and here's the derivative of my original function. That's going to be the derivative of sine, which is cosine, evaluated at f inverse of x, or inverse sine of x. So it is actually correct, although not simplified the way it's usually simplified, to say that the derivative of the inverse sine of x is 1 over cosine of the inverse sine of x, which I know is kind of weird, but it's not that big a deal. Specifically, I want to know what the derivative of the inverse sine of x is evaluated at 1/2. So I'm going to do this. Okay, well, that's going to equal, so the derivative of the inverse sine of x evaluated at x equal to 1/2. I'm going to plug in the 1/2 here, and the inverse sine of 1/2 is going to be pi over 6. So we have 1 over cosine of pi over 6. Cosine of pi over 6 is the square root of 3 over 2. So I end up with 2 over the square root of 3. So there's an example of how the derivatives and inverses work. Let me do one more, which will be very similar to when we did the one I did on the, well, yeah. So let's say we have this function. G of x is, I'm gonna make it a little bit different. Let's see, I want that, sure. Let's say g of x is sine of 2x plus 3x cubed plus 6x plus 5. No, plus 15. And I'm going to pretend like this function is invertible. It probably actually isn't invertible. I'm not going to worry about it. So let's say that g is invertible, even though it's probably not. I want to find the derivative, or I want to find g inverse prime, right? That's the derivative of the inverse, evaluated at, oh, I have to think for a second, sorry here. 15. Yeah, that should work out all right. Yeah, so again, I'm using that same idea that the derivative of g inverse of x evaluated at some x equal to a, and that's what this vertical line means. It means we're going to plug in x equal to a after we figure out the function is. It's 1 over the derivative of the original function evaluated at, usually people write like, I'm sorry, I feel like I'm making this slightly weird. One sec. Yeah. People often write g prime of b with a 1 over g prime of g inverse of a. Basically, whatever you're plugging in here, you're plugging in the thing that you had to let me say it this way. So I'm trying to find 1 over g prime of, well, x, sorry, actually there's 15, apologies here. So I'm trying to say, I want to find the derivative at g of g inverse at 15. So I need to know what value of x gets me to 15. And it's usually in these kind of problems very obvious. It's just like 0 or 1. In this case, it's 0, because g of 0 is equal to sine of 0, which is 0, plus 0, plus 0, plus 15. So since g of 0 is equal to 15, we can say that g inverse of 15 is 0. So I'm sorry if it's noisy. There needs to be yard work outside. It's a little bit loud. So the whole point there is that I'm going to take g prime, or if I'm trying to find the derivative of g inverse at 15, I'm going to do 1 over the derivative of g, but not at 15, 0, because it has to be g inverse of 15. Sorry, but g prime of that. So that's kind of how that works. So I have to take the derivative of this. So g prime of x is derivative sine is cosine of 2x times 2. Derivative 3x cubed is 9x squared. Derivative 6x is 6. Derivative 15 is 0. So there's g prime of x, and I'm going to plug in 0. We get 1 over g prime of 0. Cosine of 0 is 1 times 2. 9 times 0 squared is 0. And 6. Let's end up with 1/8. So that's the gist of this whole thing. Right? Whenever you're taking the derivative of the inverse function at some value of x, it's always going to be 1 over the derivative of the original function but not at this value of x, but the value of x that you had to input to get to that value. It's a weird thing, I'm not gonna lie. Like, it's always something that definitely threw me off in the past. It's still something I have to think about to really kind of make sure I'm getting. So let's talk about absolute extrema, and then I'll definitely get to problems 4 and 9 and one similar to them. So, also known as global extrema. So the whole idea here is that you want to find where a function, usually on a closed interval, although not always, where a function has its absolute biggest value and absolute smallest value. So for example, let's say I have a function f of x equal to x cubed minus 6x squared on the interval from -1 to 7. And I want to find where this function has an absolute maximum and an absolute minimum. And I'm sure Professor Sanders talked about the extreme value theorem and the fact that if you have a function that's continuous on a closed interval, which this certainly is, this is a continuous function, it's on a closed interval, you will always have an absolute maximum and an absolute minimum. So how do we find that? Well, we have to do two things. First thing, we have to find the critical values of the function. And the way we find the critical values of a function are taking the derivative and seeing where the derivative is either equal to 0 or where the derivative is undefined. I take the derivative, 3x squared minus 12x, and I'm going to ask myself, where is that 0 and where is it undefined? It's clearly never undefined, right? There's no division by 0, there's no square roots, there's no natural logs or any logs. So I'm just going to see where it's equal to 0. I'm going to factor out a 3x, 3x times x minus 4 equal to 0. So my critical values are x equal to 0 and x equal to 4. Additionally, when you're talking about absolute extrema on a closed interval, we always imagine the endpoints being critical values as well. So I would also say, usually people say that x equal to -1 and x equal to 7 are also critical values for this particular problem. So here's what we do. After we find our critical values, we take all of the critical values that are in the interval. So sometimes, like if, for example, if 8 had been a critical value, we wouldn't use it because 8 isn't in between the interval endpoints. So we're going to take all of our critical values and plug them into the original function, not the derivative, because we don't care what the slope of the tangent line is, we just care what the function value is. So I'm going to plug them into the original function and see what happens. And in my opinion, it really is helpful to factor the original function so that it's easier to plug into. I'm going to factor on x squared. So there's my function nicely factored. And then I'm going to start plugging in all of these. So f of 0 is clearly 0. F of 4 is, so notice I think it's definitely easier to plug it into the factor form. If I plug it in here, I have to do 4 cubed minus 6 times 4 squared, whereas here it's just 4 squared, which is 16 times 4 minus 6, which is -2, and 16 times -2 is -3. That seems way easier to me. F of -1 is going to be -1 squared, so 1 times -1 minus 6, which is -7. And f of 7 is going to be 7 squared times 7 minus 1, which is 49. And then we just decide, or we just look and see which one's the biggest. So here's the biggest one. That's where we have an absolute max, or a global max. And -32 is the smallest. So that's where we have an absolute minimum. A few things about the language here. I would say we have an absolute maximum of 49. It occurs at x equals 7. So the value is always the y value, and the place where it occurs is always the x value. In a similar way, I'd say I have an absolute minimum at x equal to 4 with a value of y equal to -32. So the minimum value, the absolute minimum value of this function is -32. The absolute maximum value of this function is +49 on this interval. And let me kind of show you, I think it's, yeah, let me grab this notes here. I think it's nice to show you this. So if we look at this function, which is All right, x cubed minus 6x squared. Zoom out just a little bit. In fact, so just let me share this with you guys. So here's the function, x cubed minus 6x squared. And we can also do this cool thing where we limit our domain. So if you put it in braces, let me see if I remember how to do this. Yeah, put it in a brace. And then I want x to be between -1. So -1 is less than x is less than, whoops, maybe that's, I thought I knew what I was doing. Oh no, there we go. Okay, I did, I just hadn't finished it. So if we look, right, we can see the very end. So clearly from the picture, the absolute minimum is right here at 4, -32. And from the picture, the absolute maximum is way over here. It's, well, it's okay. So I don't know how to do less than or equal to. Maybe let me try one thing. Yeah, okay. You just literally type a less than and then an equal to sign. So let me do that. That's better. So you do less than and then you type equals and it changes to that. Perfect, cool. So then if we click on 7 here, it's 7, 49. So that shows us that this function on this enclosed interval has an absolute maximum here at x equal to 7 with a y value of 49, and an absolute minimum here at x equal to 4 with a minimum y value of -32. So that's how that works in general. Yeah. Let me stop sharing the screen. So are there questions about that one? Let's do one more like this because there's something I do want you guys to see. I have to think real quick here. Sorry, let me just have that board real quick just to do some math. And on that, sure, we can do that. Sorry, I know I'm being like, sure. Okay. X cubed minus, so let's say we have the function g of x equal to x cubed minus 2x squared minus 2x plus 1. Yeah. On the interval from, let's say, 0 to, let's go with 5. That doesn't seem too awful. And again, I want to find the absolute maximum and the absolute minimum on this interval. So first things first, we're going to take the derivative to set it equal to 0 to find the critical points. So g prime of x is 3x squared minus 4x minus 2. And again, you should also be thinking about where it's undefined, but it's not undefined. That's the bonus. In fact, for these particular types of problems where you're finding the absolute max and absolute min, if the function is undefined, then you actually can't use this theorem because the theorem specifically says the function has to be continuous on the interval. So these ones, your critical points should never come from undefined things. That's not always true. Oh, I could, I'm gonna take that back a little bit. Yeah, sorry. So actually, I'll address that in a minute. But there's sometimes you can have a function that is continuous that still has an undefined derivative. So take it back. You could totally have, yeah, this could be undefined. We should check for that. All right. So how am I going to solve this? I guess I have to factor. So let's see. I'm factoring this. I know I'm going to have a 3x and an x because that's the only way I'm going to multiply the 3x squared. But then I have to have some combination of 2 and -1 or -2 and +1. I'm trying to make it add up to -4. So I think I want a -2 here, because that will give me a -6x. And a +2 here, because that will give me a +2x. And -6x plus 2x will give me a -4x. All right. So let's see. What are my critical values? I get x minus 2 equal to 0. Excuse me, x equal to 2, or I get 3x plus 2 equal to 0, which gives me x equal to -2 divided by 3 is -2. And then we're going to do the same thing we did. And we also, of course, I don't even write it down. We also have 0 and 5. Those are all the endpoints are always going to be something being put. So now we're going to look at, I really want to stress this, we're plugging in the points into the original function. So looking at my endpoints, g of 0 is 0 minus 0 minus 0 plus 1. And g of 5 is a little bit more work. 5 cubed is 125. Minus 2 times 5 squared is 2 times 25, so minus 50. Minus 2 times 5 is minus 10, plus 1. So 125 minus 50 is 75, minus 10 is 65, plus 1 is 66. And then I'm going to plug in g of 2. And let's see if I plug it. So I would have factored this one if I could have, well, but it doesn't, I don't think it factors. Plugging in 2, I get 8 minus 4 plus 1, so 8 minus 8 is 0, minus 4 plus 1 is negative 3. And then lastly, I stop myself before I plug in negative 2/3. And the reason why I stop myself is because negative 2/3 is not in the interval. So I don't even need to think about it, right? It's not something we have to consider. So make sure you're aware of that. The ones that aren't in the interval, we don't even worry about them. They're not fair game. So I would say that I have an absolute maximum of 66, or that's my maximum value at x equal to 5. And I'd say I have an absolute minimum value of, what's my absolute minimum value? Yeah. And where is it at? Exactly. That's exactly right. So that's how these ones work, finding the global extrema on a closed interval. He does have one homework question, which is a little bit different. We can look at that one too. Here's the attendance again, just in case you guys hadn't gotten it yet. So I do want, the words are challenging. So let's look at problem 6 for just 1 second, because I just want to point out that it's not that terrible. Let me give you a slightly different example, and then we'll talk about how you can answer his question, because it's challenging to think about unless you know what's happening here. So let's say I'm going to look at the function f of x equals to x to the 4th times e to the negative x. I'm going to have to go to the office and get some new pens. All right. So, and let's see, what's the question say? So, so actually this is kind of question 5 and 6. To find all critical points and numbers of the function f of x equals to x squared e to the negative x, or x to the 4th e to the negative x. Do note that we are not being given an interval here, right? Just the critical points everywhere. So I was going to do this. It's okay, well, my critical points, to take the derivative, I have to use the product rule. So we get 4x cubed times e to the negative x plus x to the 4th times the derivative e to the negative x, which is negative e to the negative x. And then we're going to set that equal to 0. And whenever you're trying to solve these derivatives equal to 0, factoring is your friend. In fact, my friend used to say, when in doubt, factor out. So we don't know what to do, factor some stuff. So from each of these, I can factor out an x cubed. I can also factor out an e to the negative x. So here I'm just left with a 4. And here I'm left with there's still a minus 1 left behind here. So writing this a little bit more nicely, I've got x cubed times e to the negative x times 4 minus x. All right, can anyone tell me one of my critical values? You could even say words. Yep, 4 is one of them. What else? So you bring up a good point, right? we've got this e to the negative x thing, and here's the thing that's important to know about e to the negative x. If I graph e to the negative x just on its own, just as an aside here, right? E to the negative x looks like this. And it never touches the x-axis. It has a horizontal asymptote at y equals 0. It's never equal to 0. It's never equal to 0, meaning we never get a critical value from this particular factor. So whenever you got e to the x or e to the negative x or e to the anything, or 2 to the anything or 3 to the anything, any exponential function whose base is positive, you're never going to get a critical value from that because it's never going to equal 0. So our only critical points are 0 and 4. And I'm imagining, at least this homework doesn't yet talk about relative maxima and minima, so we'll do that there. So then he asks the question, what is the global minimum of the function? And then where would it occur? So here's the thing. Usually you can't answer that question if you have, well, there is a way to do it if you have just one critical point. Because if you have just one critical point and you know it's a minimum, which we haven't really talked about yet, you can say that it's the only minimum, and so it's the global minimum. There's a little bit more to it than that. Here is what's going on with this. He kind of gives it away in the problem. And the same thing is true here. So he says in problem 6, what's the global minimum of, I'm going to say f of x equal to x to the 4th e to the negative x. Well, here's the thing. We're going to use our answer to problem 5, right? And then we're going to say, hint. Note that our function, x to the 4th times e to the negative x, is non-negative, right? This function is never negative. X to the 4th is always greater than or equal to 0. And we just talked about how e to the negative x is always greater than 0. So this function is always greater than or equal to 0. So what's the smallest it could be? Yeah. Is it ever equal to 0? It is. Where would it be equal to 0? Is it going to be at this critical point or at this critical point? I think it's going to be here, right? Because I plug in 0 to the original function, f of 0 is 0 times it doesn't matter. I get 0. Whereas f of 4 is not, right? F of 4 is 4 to the 4th times e to the negative 4th, which is some other thing, not 0. So we definitely do have a global minimum at x equals 0 with a value of 0. And again, if you want, we can totally look at the graph of this thing because it's kind of worthwhile. Let me show you the graph real quick. So turn this one off. We've got what? X to the 4th times e to the negative x. It's going to get kind of stupidly big in just a second, but oh well, it's fine. So, oh yeah, it's ridiculous. So take a look here. Share my screen. So here's the graph of x to the 4th times e to the negative x, and you can see at 0 we clearly have, well, and so actually I should introduce a little more terminology here, which I think he talked about in class yesterday, or will talk about today. Right, so here at 0, 0, we have a global minimum, right? That's the smallest value of the whole darn function everywhere. We can zoom way out and it's clearly the smallest. It's also a relative minimum or a local minimum, meaning that right there, the y value is smaller than all the y values that are left of it or right. If we go a little bit to the left or a little bit to the right, the y values can get bigger. In a similar way, at the critical point 4, we have a local maximum, right? At this point, the y value here is bigger than all the y values just to the right and all the y values just to the left. So that's what it means to be a local or relative extrema. That you're bigger than or smaller than all the things just right next to you. I would also mention that this relative maximum or local maximum is not a global maximum, right? This is definitely not the biggest value the function takes on. There are much, much bigger values way over here. So this is a local max, but not a global max. All right. So I think those are good examples of global extrema. Okay, yeah. So let's, been kind of avoiding the, let's see, 4 and 9. 9 looks interesting. I feel like I might have to think hard to make a problem that's similar but not the same. So let's go ahead and look at 4 as much as I'm dreading it. Okay. So let me ask you guys. So this is an important question. When he talked about Taylor polynomials, did he talk about the shortcut methods or did he just do it the long way? So I do need your guys' input here because it kind of affects what I say next. Anybody? All right, so I guess I'll just assume then that he did it the long way, which is a giant pain in the butt, but it is one way of doing it. So let's say I want to find the third degree Taylor polynomial. For what do I want to do here? That's kind of a pain. Sure, we'll do this. F of x equal to 1 over 1 plus x, centered at 0. 0 is pretty typical unless it's undefined there. Okay, so here's the thing about this. It's kind of just a formula you need to memorize if he's going to make you do it the long way. So here's how the formula works. The Taylor polynomial for f of x, ooh, that's not the pen I wanted. There it is. The Taylor polynomial for f of x is given by the following formula. It's equal to f of, let's see, it's f of a. There's, I can be more explicit, plus f prime of a times x minus a to the first, over 1 factorial, plus second derivative evaluated at the center over 2 factorial times x minus a squared. And it just kind of goes on this way. Third derivative at a over 3 factorial times x minus a to the third, and so on and so on and so on. And so if we're trying to find the third degree Taylor polynomial, we're trying to get the terms up to the power of x cubed. So here's what that ends up meaning. We have to find all these derivatives. I have to find the first, second, and third derivative if I want the third degree Taylor polynomial. So let's go ahead and make a list. So my function, and I think it's going to be much more convenient to write my function not as 1 over 1 plus x, but as 1 plus x to the negative first. Because if I have to take repeated derivatives, it's nicer like this. So then my first derivative is going to be negative 1 times 1 plus x to the negative second. I should think about the chain rule for a second and say I would multiply with the derivative of the inside, but that's just going to be 1, so I can kind of ignore it. And then I get the second derivative. That's going to be negative 1 times negative 2, so positive 2 times 1 plus x to the negative third. And then the third derivative is going to be negative 3 times 2 is negative 6 times 1 plus x to the negative fourth. But then I actually need all of these evaluated at the center. So I actually need f of 0, which is 1 to the negative first, which is just 1. I need f prime of 0, which is negative 1 times 1 to any power is 1. I need f double prime of 0, which is 2 times 1 to any power is 1. And I need f double prime of 0, which is negative 6 times 1 to any power is 1. How did I get the negative 1 here? I use the power rule, right? So the derivative of something to a power is you multiply by that power, and then the new power is 1 less, right? Just like the derivative of x to the fifth is 5x to the fourth. Same idea. And so now I have everything I need. I have all of these coefficients. I know that a is 0, so here's my Taylor polynomial. And I'm going to say something about it after, right? So my f of x, which is 1 over 1 plus x, the Taylor polynomial approximation, or I should say the fourth degree, I shouldn't say that. I should just say the fourth degree Taylor polynomial, sorry, third degree. Taylor polynomial for 1 over 1 plus x given by f of 0, so 1 plus f prime of 0, which is negative 1 over 1 factorial times x minus 0 to the first, plus f double prime of 0, which was 2 over 2 factorial times x minus 0 squared, plus the third derivative, which was negative 6 divided by 3 factorial times x minus 0 to the third. And then I would simplify this. So simplifying, here's what I've got. I've got 1 minus 1 over 1 factorial is 1, right? It's just 1. So I get minus 1 times x. And then 2 over 2 factorial. 2 factorial is 2 times 1, so those just cancel. 2 over 2 is 1. And you get plus x squared. And then it's going to be a minus. And 3 factorial is 3 times 2 times 1. So 6 over 3 times 2 times 1 is 6 over 6, which is also 1. So you get minus 1 times x cubed. And that would be the third degree Taylor polynomial for this function. Something worth noting. The first degree Taylor polynomial of a function is the same as the linearization of that function at the whatever point you're finding the polynomial at. So, in fact, let me write that down because I think that is something that you guys should want to know. So, the linearization of f of x at x equal to a is the same thing as the first degree Taylor polynomial centered at a. True story. We can definitely do an example. All right, let's do an example similar to his problem 1 and 2. I don't know. Let's do something similar to 2. I'm going to flip it though. I'm going to say, let's say our function is, make it a little bit different. Sure. Let's say it's 2 minus x over 2 plus x. And I want it to be centered at 0. And so I'm going to do it both ways so you guys can really see that, oh yeah, it's the same thing, whether you're thinking of the linearization or you're thinking of the first degree Taylor polynomial. In fact, it almost feels dumb to do it both ways because, like, well, let me do this. Let me write out the formula for the linearization. So here's the linearization of a function. It's f of a plus f prime of a times x minus a. Are there questions about that? Okay, I'm just going to go back to the other side. Here is the first degree Taylor polynomial. Oh, look, that's f of a plus f prime of a divided by 1 is f prime of a times x minus a. It is literally the same thing. So if someone says first degree Taylor polynomial, you can think linearization, or vice versa. If someone says linearization, you can think first degree Taylor polynomial. It is nice to know that they really are the exact same thing. It's just, and to kind of expand on that, what this means is that we're thinking about using a linearization to approximate a function with a straight line. Well, the Taylor polynomial takes that as many steps further as you want and says, oh, instead of using a straight line to approximate a function, maybe I'll use a second degree polynomial, a parabola to approximate a function, or a third degree, or a fourth degree, or whatever degree I want to approximate a function. So it's a better approximation the further we go, but it's also more work. So let's find the linearization of this function at this point. All right, so I need to do a couple things. I need to find f of 0. Well, that's easy. It's 2 over 2. And find f prime of 0. Before I can do that, I need to find f prime of a. Sorry, f prime of x. So f prime of x, I'm going to use the quotient rule. It's going to be the bottom times the derivative of the top, which is -1, minus the top times the derivative of the bottom, which is +1, all over the bottom squared. Usually when you have something like this where it's like almost the same but opposite signs, I feel like the x's usually cancel on top. Let's check. I get, let's see, so distributing the -1, I get -2 minus x, and distributing the negative here, I get -2 plus x. I don't multiply at the bottom. The minus x and the x do cancel, so I get -4 over 2 plus x squared. And then if I plug in 0, f prime of 0 is -4 over 2 squared, which is just -1. All right, I've got all the pieces. Now I'm just going to throw everything into this formula. So my linearization is f of a, which is f of 0, which is 1. And then plus my f prime of a, which is my slope at 0, which is -1. Times x minus a, which is x minus 0. And simplifying that, I see that my linearization is 1 minus x. So that's just the slope of the equation of the tangent line. And let's go ahead, let's look at Desmos again, because I think it's worthwhile. So if I want to graph these things, right, I can graph the original function. Turn this one up. Okay, so here's my original function, which is 2 minus x over 2 plus x. And then if I graph the other thing, 1 minus x, it should give me the tangent line at the point 0, 1. So I do that. There we go. In fact, actually, to kind of expand on that, let's look back at this previous example. So, yeah, so I'm going to graph this just so you guys can see this, because I think when I was learning Taylor polynomials the first time, it was definitely something that felt weird. I'm like, what are we doing with this? But the idea really is you're just using these polynomials, to approximate functions that are more complicated. So 1 over 1 plus x, looks like that. And then I can use, so here's a 0, so I'm just going to increase term by term. So my first term is 1, right? In fact, so this happens to be, so here's y equal to, oh, that's not very exciting. Let's do this. All right, so there's the 0-degree Taylor polynomial, which is not very interesting. Doesn't do a great job of approximating the function anywhere other than at the point it's at. But then if we subtract, if we go to the next term, so there's the 1st-degree Taylor polynomial. Does maybe a little bit better job, right? You can see that if you're right, in here, maybe between -0.5 and +0.5, it's still an okay approximation. But now if we add on the next term, here's the 2nd-degree Taylor approximation, and look at that. And I should say, right, it's the approximation is of course going to be good at the center or at the point we're approximating at, and as you move away from that, it's going to get less good. But you can see here, right, this is a much better job of approximating this function than the straight line was. And if we add on the next term, oops, look at that, it's even better. And if we keep, and so I will tell you this particular Taylor polynomial, the terms do just keep alternating signs. So it's going to be plus x to the 4th minus x to the 3rd. If you keep on adding terms, it just looks even, right? It's just you're getting nicer and nicer approximations for more and more of the function. And so you can keep doing this forever. I kind of want to because it's kind of fun. But right, you can kind of see like as you do more and more, it gets to be a better and better approximation of this function. So that's the idea of a Taylor approximation. It's literally using a polynomial to approximate a non-polynomial function around a particular point. So hopefully that helps you guys have a better understanding of what Taylor polynomials are. They are useful. We definitely do use them sometimes, like when we're integrating functions later on in Calc 2 or 17b, whatever you want to call it. Sometimes functions can't be integrated, so we use a Taylor approximation for them and then integrate that, which is really, really straightforward. So that's kind of one application of Taylor polynomials, is that they're easy to work with and they do a good job of approximating more complicated functions. All right, let's see. Let me take one thing about 5. Yeah, okay. Okay, so let's see. Someone asked about number 9, which I can definitely. So number 9 looks like it's meant to be challenging, but I also feel like it's not one that I can make up one that's going to be super similar. So let's work through the beginning of number 9, and I'll see if I can stop myself from finishing it. Sorry. So here's what number 9 says. Find all the critical points of the function f of x equals to 1/2 x squared minus 2 natural log of x plus x plus, minus x plus 3. Interesting. All right. So first things first, if we're going to find the critical points, the critical values, we have to take the derivative and set it equal to 0. That's always our first step when we're finding critical points. I guess I should also say, right, or undefined. Now, we'll talk about this in just a sec because there is some fine print we need to be aware of here. So what is my derivative? Well, your 1/2 x squared is 1/2 times 2x, which is just x. What's the derivative of the natural log of x?
1/x.
Thanks. You guys are alive. It's nice to talk to you. I kid. And then the derivative of negative x is -1. And so we're going to set this equal to 0. And I might simplify it a little bit, right? X minus 2 over x minus 1 equals 0. So let me ask you guys, and this is kind of a challenging question. Is x equal to 0 a critical point or not? And there are good arguments to be made for either answer. So let me point out, if x were to be 0, we would have division by 0, which would be undefined. So f prime of 0 is undefined. Now here's the thing. To be a critical value, you technically have to be in the domain of the original function. And 0 is not in the domain of the natural log of x, right? It's the natural log of 0 is undefined. So 0 is not a critical point here. Just as an aside, what if my function was something else? What if my function was g of x equal to the cube root of x minus 8? Which definitely is defined everywhere, right? You can take the cube root of positive numbers, you can take the cube root of negative numbers, they're all defined. Cube root of 1 is 1, cube root of negative 8 is negative 2, and so on. But the derivative here, well, this is x to the 1/3 minus 8. And the derivative of x to the 1/3 minus 8 is 1/3 x to the negative 2/3 minus 0. Or 1/3 times x to the 2/3. And this function, this derivative, is undefined at 0. Right, if I plug in 0 for x, I get division by 0. But here, x equal to 0 is a critical point, because the original function is defined at 0. So as long as the point is in the domain of the original function, it's a valid critical value. If it's not in the domain, then it's not a critical point, even if it makes the derivative 0 or undefined. So something to be aware of. So how would you finish this problem? I would multiply everything by x. So I multiply this by x, this by x, and this by x, and I get x squared minus 2x minus 1. Maybe I missed a sign somewhere. No, that looks right. And so then you have to set that equal to 0 and solve. Okay, so I mean, you can solve this equal to 0. You're going to have to use the quadratic formula though, but you will get values. And then here's the thing. So this problem is on the interval from 1 to e. you have to make sure your critical values are in the interval. And my bet is that one of them is going to be in the interval, like the one that's 1 plus some square root of something, and the other one's going to not be in the interval. It's going to be 1 minus something, and 1 minus something is less than 1, and 1 is the endpoint. So find the critical points. 0 is not a critical point, but you'll get 2 critical points from the quadratic formula, and then I'm pretty darn sure one of them is in the interval and one of them is not. So the answer, and he even writes it in the problem right here. He says, remember that anything outside the interval does not count as a critical point. He didn't close his parenthesis though, which is terrible. Not really, that's not that terrible. I'm just kidding around. Okay, that's all I've got for today. I imagine we will continue talking about this all on Monday. I do see that there is a Newton's method question on there, which we should probably go over something like that on Monday. And yeah, so think about what kind of questions you guys have for Monday, and I will see you then. And if there are other things you need to see before Monday, shoot me a message or start a discussion on Canvas, and I will see if I can make a video covering that kind of thing. All right, have a nice weekend, you guys. It's week 7 in the bag. 3 more to go. You're very welcome. I'll talk to you guys next week.